Okay, here's a video, I guess, answer key to the redox equation or the redox review sheet that I gave out in class. I thought I'd do a video just so that you might be able to pick up a little bit more. So feel free to fast forward to whichever question you're interested in. These definitions, these are just ones that you can get from your text or from your notes. You can define those. These two here, oxidation reduction, redox reaction, they both really mean the same thing. Okay, this question, write a net redox equation for the following. Include voltage and indicate spontaneity. Okay, aqueous, magnesium, so I'll do A first. Aqueous, so there's water. Magnesium chloride, it's ionic, it's in water, so it dissociates into magnesium ions and chloride ions. Make sure that when you're writing these that you don't just write Mg, because Mg by itself is a solid, but this isn't. This is an aqueous solution. These will dissociate their ions. Is placed in an acidic solution, acid, of potassium permanganate. Again, ionic compound, so that it'll dissociate the potassium ions and permanganate ions. Okay, I've done enough of these to know that that'll be my SOA. And let me just look at my chart here. MnO4, 8 hydrogens, 5. Okay, so it'd be MnO4 minus plus 8 hydrogens plus 5 electrons yields Mn2 plus I believe it's 4 waters. I think that's correct. So that is my SOA. And now I need to find out my SRA. So my SRA on the right side, it could be chloride ions. There's chloride ions. Oh, but water's right below it. If I scroll down a bit, yeah, there's magnesium down here, but I had magnesium on this side. For an R8, it has to be on this side, so that one doesn't count. I think the one I have to go with is water, up top here. So water. So I write 2 waters give me oxygen, 4 hydrogens. Okay, so 2 waters. This will be for my SRA. That's this one, SRA. So 2 waters, and remember you have to write it backwards, will produce, what was it again? 2 waters. Oxygen, 4 hydrogens, and 4 electrons. Whoops. Oxygen plus 4 hydrogens plus 4 electrons. Okay, so I need to write the whole redox reaction. So I need to balance these. I've got 5 electrons on that side and 4 on this side. So I'm needing to go to 20. So I'll take this one and times it by 4. I'll take this one and times it by 5. And hopefully I'll remember that. Okay, so I'm going to have 4 MnO4s. 4 times 8 is 32 hydrogens. I forgot my minus there. 20 electrons, those will balance or will cancel each other. And then 5 times 2 is 10 waters. 10 waters. And that's all on the left side. Okay, the right side. 4 Mn2 pluses plus 4 times, well, that was 4 waters, I think. Whoops. 4 times 4 would be 16 waters. And then 5 times that will be 5 oxygens. And 5 times that will be 20 hydrogens. And 5 times 4, that's the 20 electrons, they cancel out. Now, this is good so far, but if I notice that there's the same compound on each side, I can simplify that. So net, there would be, I've got 32 on this side, 20 on this side. So net, I would have 12 on this side. So I'll rewrite this sort of in a simplified form. So it'll be 12 hydrogens. How about waters? 10 waters, 16 waters. So the net would be, let me write this other one down because it's not on both sides. 10 here, 16 there. My net would have 6 waters on that side. I still have my 5 O2s, and the hydrogens, they cancel out. with the other ones. So that would be my net redox equation for that first one. Let's do the next one. Copper is placed in calcium chloride. So this is B. Copper, so it's copper solid, is placed in calcium, a solution of calcium chloride. They say solution, I'm writing water. Calcium chloride's ionic, so it'll separate into calcium ions and chloride ions. Okay, again, I go to my chart, see who's my SOA, SRA. Copper. Where's my copper? Uh-oh. There's copper right there. And water is up there. So copper is my SRA. Copper, SRA. Okay, on the left side I got calcium. Oh, those are chloride ions. Calcium and water. Okay, calcium's way down below. There's calcium. Oh, and here's water right there. So I have to pick the one higher up on the left-hand side, so it's going to be this one. So 2 waters plus 2 electrons. Let me get that in a spot where I can see it. Where was it? Shoot. 2 waters. There it is. Okay. So I've got 2 waters. This would be my SOA. 2 waters plus 2 electrons yields hydrogen plus 2 hydroxides. And then that's my SOA. My SRA written backward will be copper solid yields copper 2 plus 2 electrons. The electrons are even Steven, so they cancel out. And so I'm going to have 2 waters plus a copper solid producing hydrogen plus 2 hydroxides plus a copper ion. Okay, hopefully you're feeling okay with those. Let me go up to the top here though. I think I forgot to do my my voltages. Let me just go and fix that. So the voltage for MnO4, where was it? Plus 1.51. So this is positive 1.51. And the water one, where's water? Right there, 1.23. Oh, but I have to change its sign, right? So it'd be negative 1.23. So when you subtract, that'll be 11 minus 3 is 8, 28. Positive. I hope that's right for that one. I don't remember that. I think it's right though. Okay, and the last one, this water, is that right? Did I put water at the right? Water on the right-hand side. Yeah, I read it right. Okay, next one. Water, this is on the left-hand side this time. So water on the left-hand side, where was that? It's hard finding these all the time. There's water right there. Negative 0.83. And it's an SOA, so I have to leave it as is. And the copper one, where's the copper one? Right there. And this one I have to change around, so it'll be negative 0.34. Negative 0.34. Okay, they're both negative, so I add, that'd be a 7, that'd be an 11, and this would be negative. So this reaction here is non-spontaneous, whereas this one at the top, because it's positive, would be spontaneous. Okay, so that is that question. Next question, oxidation states for these. Oxidation states based on hydrogen, when it's connected with something else, is always a 1 plus. Oxygen, when connected with something else, is always a 2 minus. Everything else you can determine based on these. The only time that these are 0 is if they were diatomic and they were by themselves. Okay, so that would be 0, or oxygen would be 0 like that. But if they're hooked up to something else like all of these ones are, oxygen's always 2 minus, hydrogen's 1 plus. So I have 2 oxygens, so it's 4 minus, and hydrogen's a 1 plus. So I need to figure out something for nitrogen so that this adds up to 0. So I have a 1 plus, a 4 minus. The nitrogen must be a 3 positive. 1 plus 3 is 4. 4 take away 4 gives me 0. Let's do this one. 3 oxygens, so this would be a 6 plus. Sulfur would be a 6 plus. Okay, next one, oxygen's a negative 2. There's 2 of them, so that's negative 4. So to even this thing out to 0, nitrogen would have to be a plus 4. HNO3, there's 3 oxygens, so that's a negative 6. Hydrogen's a positive 1, so this nitrogen here has to be a positive 5. Last one, this one has to add up to negative 2 because this is a complex ion. And so I've got 4 oxygens, that'd be minus 2 times 4 would be a minus 8. But the whole thing has to add up to a minus 2, not 0 like these other ones. So sulfur would have to be a positive 6. That would be its oxidation state. Next question, so based on oxidation states, which is the OA and which is the RA? Okay, these guys are by themselves, so their oxidation states are 0. Over here, oxygen's a 2 minus, there's 3 of them. So 3 times a 2 minus, that would be a 6 minus. So this stuff from iron has to be a 6 plus. But there's 2 irons, so each one of them is a 3 plus. So if I look at oxygen here to over there, it went from 0 to 3 plus, it must have lost electrons. A loss of electrons is oxidation, and the thing that does that, this guy here, is your strongest reducing agent. Okay, so that means the oxygen goes from 0 to a 2 minus, must have been gaining electrons, so oxygen, this oxygen right here, to go from there to there, it gained electrons, therefore that oxygen there is the oxidizing agent. Okay, let's look at this last one. Oxygen's a 2 minus, hydrogen's a 1 plus, oxygen's a 2 minus, so that'd be a minus 4 there. So carbon would have to be a plus 4. Okay, oxygen's a 2 minus, so that's minus 6. In this case here, I have to get to 2 minus, so that carbon has to be a 4 plus. And this hydrogen's an ion, so it's a 1 plus. If you take a look at every element there, there's no change. Carbon's a plus 4, oxygen's always a minus 2, hydrogen's a 1 plus. If there's no change, this reaction is not a redox reaction. So there's no oxidizing agent or reducing agent. Question 5, definitions. Get these from your text or from your notes. An electrochemical cell and a galvanic cell, I think they're both there might be slight differences, but basically they are cells that from chemicals you can produce electricity. Okay, draw an electrochemical cell composed of the following stuff, label all the parts. Okay, so I have silver and silver. I've done enough of these that I know that this silver here is going to be my strongest oxidizing agent. And then on the right side, if you look at your chart, zinc is going to be the furthest one down on the right. Where's my zinc? There's zinc right there. There's nobody in there that's further down than the zinc, including water. Okay, so there is water here too, but your SOA and your SRA are not water. So this is my SRA. Okay, so when we build our thing, beaker, I always put my OA over on this side, so I've got a cathode there. My OA is what's going to be floating in the solution. Okay, be my silver ions. And then the cathode, this thing here, the electrode that's there, will be made of silver. Okay, I've got my salt bridge there. I've got another electrode over here, and I've got a wire that connects the two. And over on this side, the electrode or the anode will be made of zinc, and my zinc ions will be in there. Okay, cathode, anode, electrons are flowing this way. If you look on your chart, look up silver's number, put zinc numbers backward, and you can get what the voltage is for that cell. Oh, maybe we might as well do it. Zinc's voltage. Where's zinc? I had zinc. Negative 0.76, but I have to change that to positive. So positive 0.76. And then the one for silver is way at the top. Where's silver? Silver's right there. Positive 0.80, 0.80. So if you add those up, 1.56 will be the voltage. Okay, so that is our voltage. It's positive, therefore it is a spontaneous reaction. Okay, I think that we have, oops. Oh yeah, I think we have indicated all of those things. All right, let's try the next one. Oh, there were two questions. Is there another question? Oh, here's the other question. Whoops. Okay, a lead 2 plus, Fe 3 plus, Fe 2 plus. Oh, there's no electrode there. Let's put in one. Let's maybe put in a carbon one, an inert electrode. Okay, so I need to look at all these species and see which one's highest up on the left, lowest on the right. Okay, all right, so lead and iron. Okay, so here's the top. Lead and iron. Oh, there's iron 3 plus right there. That's going to be my SOA for sure. So iron 3 plus is my SOA. Okay, and then lead is probably way down here. Here's lead sulfate. Oh, there's lead right there. So lead will be my SRA. Okay, so lead is, this one is my SRA. All right, so to make my cell, beaker, porous cup, electrode, wire. Okay, my SOA goes in solution here, so this be Fe3 plus. And then, oh, this is the one that has the inert one. So this electrode will, the cathode will be a carbon or an inert one. The Fe2 plus ions, they'll be in here as well. 2 plus ions, they'll be in here as well, but as electrons come in, iron will accept them and change from an iron 3 plus to an iron 2 plus. Typically when that change happens, there might be some kind of a color. You don't have to worry about that, but that's how you can identify what's happening. Okay, on this side then, the electrode, the anode would be called lead, or would be made of lead, and the ions floating in here would be Pb2 plus. If I look at the numbers, Pb, where it was right here, right there, is negative 13, but I have to switch that around. So it'd be positive 13. And then the iron 3 plus is right there, positive 0.77. So positive 0.77. If I add those together, I think that comes out to 0.90 volts. So that would be spontaneous. It's positive. It'd be spontaneous. It'd produce electricity for you. Okay, in question 7, now they're asking you to go back, and I'll just do one of them, but you have to go back to question 6 and answer this question. So you've got amps, you've got time, and you're looking for the mass of each reducing agent. So for this first one, the reducing agent is the zinc 2 plus right there. This is my oxidizing agent right there. Oh no, it's not my reducing agent. My reducing agent will be the zinc, right? So zinc is my reducing agent, so that's the one I'm going to look at. So really the equation is zinc as a reducing agent produces zinc ions and 2 electrons that it gives to the wire. That's the reaction happening. But given this information here, I need to go and do my formula. Moles of electrons is equal to IT over Q. The amperage is 10, and that's 10.0 coulombs per second. Time is 10 minutes, and there's 60 seconds in a minute, so 10 times 60 would be 600. So times 600 seconds. And then Faraday's constant, 9.65 times 10 to the fourth coulombs per mole. So the coulombs cancel, the seconds cancel, I'm left with moles. All right, pull out the calculator. So it's going to be calculator. So 600 times 10 be 6,000 divided by 9.65 times 10 to the fourth equals, okay, so I get 0.06217, etc. moles of electrons. So that's moles of these guys. Now I have to do my mole ratio, so I want to find moles of zinc, not electrons. So it'll be 0.06217 moles of electrons times 2 moles of electrons come from 1 mole of zinc. 1 mole of zinc. So I'll take that first number then and divide it by 2. So I'm getting 0.031088, etc. moles of this time zinc. And now I need to find the mass of zinc. So the mass of zinc using our formula is moles times molar mass. So the mole 0.031088 multiplied by, that's moles, the molar mass of zinc, which is way at the top here. Let me find it. Uh-oh. Zinc. Do you see zinc anywhere? Right there. 6539. So 6539. So times 65.39 equals 2.03, and I think it's 3 sig figs, and this would be grams, because this is grams in every mole of zinc. Moles cancel, left with grams. Okay, hopefully that helps with that question. Last question, molten copper, molten copper bromide. So, and I should have in here, the name is improper because copper could be a 1 or a 2. I'm assuming it's a copper 2 bromide, but I needed to put that in there. So if it's molten, means there's no water, and molten ionic compounds separate into their ions. So I'd have copper ions and I'd have bromide ions. If you look on the chart, the copper ions are the ones that are on the left. They'd be the strongest oxidizing agent. So I'd have copper 2 plus 2 electrons producing copper solid. And then the bromide, the only option for it would be for it to be on the right hand side. Where's my chart? Oh, bromide. That's up here somewhere. Oh, right there. 2 bromides gives me bromine plus 2 electrons. So 2 bromide ions produces bromine plus 2 electrons. Fortunately, they're both 2 electrons, so I can write that out. The question actually just asked what the voltage is, but might as well write the thing out. So copper 2 plus ions plus bromide ion will produce copper solid plus bromine, and the electrons cancel. So now to do voltage, the bromine one right here, but I have to write it backwards, is negative 1.07. Okay, and the copper one is right there, positive 0.34. Positive 0.34. So I have to subtract these two numbers. 107.34 be 66.59 about? No, can't be. Maybe. 1.07 minus 34. I guess I have a calculator. There's a 3. This would be a 7. 0.73. Negative 0.73. Negative indicating it's not going to happen on its own. Or in other words, if I apply that much voltage, this reaction will happen. Okay, hopefully that helps you out with the review.